Hi everyone. So today we're going to look at buffers. So when we're talking about the various biological processes that occur in our body, we have to take a look at buffers because a lot of enzymes and cellular processes are dependent on the idea that aqueous solutions exist that don't want to change their pH, because if there is even a slight change in that pH, it can affect the whole process altogether. A good example of this is the pH of blood. It exists in a pH range of 7.35 to 7.45, and even just 0.5 units in difference to that pH range can cause a person to become unconscious and die. So I've included a table here that shows the different types of fluids that are in our bodies and the specific pH ranges to those types of fluids. Now, the main takeaway you want to get from what buffers are is that they're aqueous solutions that resist the change in pH when small amounts of acid or base are added. So when you start adding hydronium ions or hydroxide ions, you want to make sure that there's not much changes in that pH range, and that way you're preventing any kind of sudden change to the process that requires that buffer in order to exist. So the buffer capacity refers basically to the amount of moles of an acid or base a buffer can react with until it can no longer resist any changes to the pH. So when we're dealing with buffer solutions, we're usually dealing with a weak acid and its conjugate base, or a weak base and its conjugate acid. So I've included two equations here that showcase that type of buffer reaction. So you have your acid reacting with your conjugate base, and you have your base reacting with your conjugate acid. Okay, and when we're looking at acid buffers, we're looking at a solution that deals with a weak acid, so HA, and its conjugate base, which is A minus. So I've shown that equation right here, and you can see that it kind of goes back and forth because it's in equilibrium, and essentially it's going to either produce hydronium ions and your conjugate base, or it's going to produce water and your weak acid. So if we look at an example here that's provided, we have an acidic buffer that has 0.1 molarity of acetic acid and 0.1 molarity of sodium acetate. We can ignore the sodium ions because they're just spectator ions, but we want to focus on the reaction that's occurring between the buffer, which is the acetic acid and the acetate. So we know that it's going back and forth, and when it's going back and forth, we're producing hydronium ions, and then we're releasing it to just form water and the weak acetic acid. So this buffer specifically has a pH of 4.74. Now what happens when we add a small amount, which is 0.01 moles of HCl to the solution? Well, HCl is considered a strong acid and it's going to release hydrogen ions. But those hydrogen ions are going to be neutralized by the base, and the base being our acetate. And so when that happens, it's going to neutralize it into forming our weak acetic acid. Now, when we're talking about pH changes by adding a small amount of sodium hydroxide, what ends up happening is the sodium hydroxide produces hydroxide ions, which is a strong base, and that gets neutralized by the acid in the buffer, so our weak acetic acid. And so that neutralizes the hydroxide ions to form acetate. And in both cases, what's happening is our equilibrium is being reestablished so that it's always moving between the acetic acid and the acetate. And so there's going to end up being very little change to our buffer's pH of 4.74. So we can kind of understand how this works by doing an example. So we have the same situation. We have 0.1 molarity acetic acid and 0.1 molarity sodium acetate with a pH of 4.74. The question asks us, by looking at this equilibrium equation of the buffer, they want us to know what happens to the pH when we add 0.01 moles of HCl and we have 1 liter of the solution at hand. So what you want to do, first of all, is identify what kind of change is occurring to the buffer. So we know that we are adding HCl, and HCl is an acid, so it's going to release hydrogen ions. So that hydrogen ions is going to react with our acetate ions in solution, and it's going to get neutralized to form acetic acid, aqueous. And so before we get started into determining the kind of concentrations we have once the equilibrium is reestablished, we want to identify the type of moles that we're going to have, because we know that there's a change in moles with the addition of the HCl. So when we create a table to show what happens before addition in terms of the molar amounts, we know that our acetate consisted of 0.1 moles, right? And that's was written right here. And then we know our hydrogen ions produced about 0.010 moles. And we know our acetic acid produced 0.10 moles, and that we derived from this information here. So now we want to know what kind of change occurred between our moles, and we know that if this is how much moles of our acid were added, it's going to change the amount of acetate that we had, right, by minus 0.010, and that means that we're going to lose the amount of hydrogen ions we had, and we're going to end up getting acetic acid by that same molar amount. Okay, and so then if we're going to calculate how much moles are present after the addition, we're going to get 0.09 moles, right, from the subtraction of what we had initially to the change. We're going to end up with 0 moles of our hydrogen ions, and we're going to end up with 0.11 moles of our acetic acid. So this can then be used to help us derive the concentrations of our buffer once it's been reestablished, once the equilibrium has been established. So the equilibrium will reestablish between the acetic acid and the acetate. Okay, so we know that the buffer equilibrium is acetic acid plus water produces acetate, that's aqueous, and hydrogen ions, right? Because it's an acidic buffer. And so we can create a Rice table for this buffer reaction. And we know that we have a 1-to-1 ratio of our weak acid, our conjugate base, and our hydronium ions. We also know the initial concentrations when the equilibrium is established. We know the acetic acid amount is 0.11. We know that the acetate amount is 0.09, and we know the hydronium ions is 0. And then we can start establishing the change in concentration. We know that the acetic acid is going to change by an X amount, and that decrease is going to be an increase in the acetate and the hydronium ions. And so we can create an equation that represents the change in equilibrium for each of these. So it's going to be 0.11 minus X, 0.09 plus X, and then X. Now that I have this information, I can end up calculating my ionization constant of my acid, which is just the concentration of my products, being my acetate ion and my hydronium ion, over the concentration of my acetic acid. And so I'm going to plug in the values that I know for acetate, for hydronium, and for acetic acid. And I know that the ionization constant for my acid, and my acid being CH3COOH is 1.8 times 10 to the power of negative 5. Okay, but we're going to use the rule of 500. And based on this rule of 500, we can say that this is negligible and this is negligible. Okay, and if that's the case, we can create a new constant, or a new equation for our ionization constant of 0.09 times x over 0.11. And that equals 1.8 times 10 to the power of negative 5. And with that said, I can solve for x, right? I would multiply this whole thing by 0.11, and then I would divide this whole thing by 0.09, and I end up with 2.2 times 10 to the power of negative 5. And now, because I have this information, this is my x, I know that the x represents the concentration of my hydronium ions once equilibrium is established again. So I can say that this is equal to my hydronium ion concentration. And because I know this, I can find the pH, because it's just the negative log of my hydronium ion concentration. So I'm going to plug that value in, and when I do that, I end up getting 4.66. So that is the change in my concentration. That's what my new pH is for my buffer, because I added that 0.01 moles of HCl. But the question says, how much did it change by? So I know my pH final is going to be subtracted by my pH initial. My pH final was 4.66 and my pH initial was 4.74. So when I look at the difference, I'm going to end up with negative 0.08, which means that my pH dropped by 0.08. And when you think about it, that's a small drop. That means that there's not that much change in my pH. So my buffer was really good at making up for that small addition of acid and strong acid that was added. Okay? Now, we can continue that understanding of buffer capacity by looking at Henderson-Hasselbalch equation. So when we're talking about buffer capacity, we don't want it to exceed past a unit of greater than 1. And when we do, we can also use the Henderson-Hasselbalch equation to calculate the pH of our buffers, right? And so, like I said, we don't want our buffers to go beyond a change in the pH greater than 1 unit. So when we're looking at the Henderson-Hasselbalch equation, we have a pH is equal to the pKa plus the log of our conjugate base, the concentration of our conjugate base, over the concentration of our conjugate acid. Now, the most effective buffers are when the pH is equal to your pKa, which then means that the concentration of our acid is equal to the concentration of our conjugate base. And the reason that that's important to remember is that if the concentrations are approximately equal, then when we plug them in and take the log of it, we're going to have them be equal to 0, which means that this is negligible and that our pH is equal to our pKa. And those are the ones that are the most effective type of buffers. So we can see that here when we look at example 2. So example 2 is using the same situation as before, right, with an acetic acid and sodium acetate with a pH of 4.74. And we have the equation that shows the equilibrium between this buffer, this acidic buffer. And they ask us what happens to the pH change when we add this small amount to it. So I still go ahead and I establish the change in my molar amounts based off of this new addition, this new molar addition of HCl, and I end up figuring out what my new molar amounts are. And then I know that because equilibrium is established, utilizing this new equilibrium equation, I can then take my amounts and I can plug it in. And I notice that my concentration for my conjugate base and my conjugate acid are very similar. But even so, because they are very close, there's not going to be much change in my pH. And when I plug it into my Henderson-Hasselbalch equation, I end up getting the pH, which is 4.66, and that is exactly what I found in practice question 1. So this is another way for me to determine the pH of a buffer. So let's expand our thinking of this to practice question number 2. So practice question number 2 asks us to explore the same acidic buffer, but they want us to calculate the pH of this buffer solution. So we're going to calculate the pH of this buffer solution, and in order to do so, we first focus on the equation that represents this buffer, which is the acetic acid plus water forms acetate and hydronium ions, and it's in equilibrium, so it's going to go back and forth. And we now create a Rice table based off of this information. So we know our weak acid, our acetic acid, is with a molar ratio of 1 to 1 to 1 with acetic acid, with acetate and hydronium ions. We also know that the initial concentration of our acetic acid is 0.1. And we know that for our acetate, it's also 0.1. And we know our hydronium ions have not been produced yet, so it's 0. We know that there's going to be a change in the amount of our acetic acid, and that same amount that's decreased is going to be increased for our acetate and our hydronium ions. And so if we're going to establish what the concentration is at equilibrium, it's going to be 0.1 minus x, 0.1 plus x, and then x. Now we can sub that into our ionization constant. And we know that for our ionization constant of the acid, which is acetic acid, it's going to be 1.8 times 10 to the power of negative 5. Now we can use the 500 rule again, okay? And using this rule, we can assume that this is negligible and this is negligible. Okay, so we can then create a new equation for our Ka, which is just 0.1 times x over 0.1, which equals 1.8 times 10 to the power of negative 5. Now, if you notice, our concentration for our conjugate acid and our base are equal to each other. So with that said, I can cancel these out, and I end up with x equals 1.8 times 10 to the power of negative 5. And like I said, the x represents our hydronium ions, so we know that this is the concentration of our hydronium ions. And now if I want to find the pH, I can plug that in. And I get 4.74. Now, it's important to note here that our concentrations of our acid and our conjugate base were equal. And because they were equal, what ended up happening is our pH was just equal to the negative log of our ionization constant, because that's what our ionization constant was. So when our concentrations are equal, okay, so when the concentration of our acid and the concentration of our base are equal, we can say that the pH is equal to the negative log Ka, and we also know that this represents our pKa. So then therefore, the pH is also equal to the pKa. Okay, so that brings us to this next part, we can actually determine the pH values of buffers when the concentrations of our acid and our base are equal. So if we have this buffer right here, and this is our Ka, our ionization constant for our acid, if we plug that Ka into here and take the negative log of it, we are going to get our pH. We can also get our pKa because, like I said, the pKa is equal to the negative log Ka. So if I take the negative log of this, I end up getting my pKa, which is going to be 3.18. And this is going to be equal, so it's going to be 3.18. Same thing here. If I take the negative log of this, I end up getting my pKa, which is 4.74. And that's going to be equal as well, and so on and so forth. So just remember, when you're calculating the pH of a buffer change, you can always use the Henderson-Hasselbalch equation. And remember, if your concentration of your acid and your conjugate base are equal, then you don't even need to worry about this portion of the Henderson-Hasselbalch equation because your pH is going to be equal to the pKa, and these are usually when the buffers are the most effective. Okay, so have fun and enjoy doing some buffer problems.